Dear students, myself Dr. Mallikarjun S. Biradar, Assistant Professor in Mathematics, Government First Grade College, Masurakalland. Dear students, already in the previous classes we have discussed about Eulerian graph, Hamiltonian graph, even we have given the characterization of Eulerian graph. Very interesting thing is that for the Eulerian graph there is a characterization. That is, you know already what is Eulerian graph. The graph is said to be Eulerian if it contains an Eulerian cycle. So definition is different and the characterization is different. If I draw a graph on the board, on the plane, we must be able to identify whether that graph is Eulerian or not. For that we have got two characterizations. One characterization, interesting characterization is a graph is Eulerian if and only if degree of every vertex is even. In a graph, any graph is given, if you observe the vertices, if all vertices are of even degree, then obviously that graph is Eulerian. So like that, later on we have discussed the concept of Hamiltonian graph. Very simple concept. A graph is said to be Hamiltonian if there is a Hamiltonian cycle. So what do you mean by Hamiltonian cycle? A spanning cycle of G. A spanning cycle, or in other words you can say a simple cycle containing all vertices of the graph. Any graph which contains a spanning cycle or a cycle containing all vertices of the graph is called a Hamiltonian graph. Though the concept is very simple to understand, very easy to define, and it is very easy to understand. For example, this is an example of a Hamiltonian graph, because this graph contains a cycle containing all vertices of the graph. Similarly, you can take another example. This one, there is a cycle containing this vertex, there is a cycle containing all vertices. Okay, so this is also a Hamiltonian graph. So it is very easy to define. Now the thing is that if I draw any graph on the plane, you must be able to identify whether that graph is Hamiltonian or not. Like there is a characterization for Eulerian graph. Is there any such a characterization for Hamiltonian graph? So once again I want to repeat, the concept of Hamiltonian graph looks like very simple. Very simple. A graph is said to be Hamiltonian if there is a Hamiltonian cycle or a cycle containing all vertices of the graph. You may say that several times I am repeating this concept. Okay, so it is very easy to understand the definition. So thing is that till today there is no a general characterization for Hamiltonian graph. So we have got a general characterization for Eulerian graph, but there is no a general characterization for Hamiltonian graph. It implies, if I say a connected graph G is Hamiltonian if and only if G or any conditions on G. Is there any such a result? If we think in this way, because you are all students, so you just try to understand what could be the general result. A connected graph G is Hamiltonian if and only if. It implies if you consider any Hamiltonian graph, that graph must satisfy these conditions. On the other hand, conversely, if any graph which satisfies these conditions must be Hamiltonian. So till today there is no such a result. So in graph theory, this is the major unsolved problem. So you may realize, though the concept is very simple, but its characterization, till today there is no general characterization for Hamiltonian graph. So you are all young mathematicians. So you may think in this direction, and if you get such general characterization, then it will be considered as a standard result in graph theory. Okay, but though there is no general result till today, but there are certainly some necessary and sufficient conditions on Hamiltonian graphs are they? It implies if a graph G is Hamiltonian, then that graph satisfies so and so condition. Very simple, straightforward. If G is Hamiltonian, then G satisfies so and so condition. Or some other results are like that. If G satisfies so and so condition, then G is Hamiltonian. One-sided the results, these are all. If it is so, then it is so and so. But there is no general result till today. Okay, so this is the major unsolved problem in graph theory as well as unsolved problem in mathematics. Okay, so you are all young mathematicians, so you may think in this direction, and if you are able to get a characterization for Hamiltonian graph, as I said, it will be a standard result in the field of graph theory. Okay. Now, what are the properties, or you can say necessary and sufficient conditions for Hamiltonian graphs? Okay. So first we consider one theorem as a result. One theorem. Say this is the fourth theorem, I think. In continuation, if we think this is the fourth theorem. So the statement is like this: if a graph G is Hamiltonian, if a graph G is Hamiltonian, then for every non-empty proper subset S of the vertex set Vg, K of G minus S is less than or equal to mod S. So what is the meaning of this? Where K of G minus S is the number of components in G minus S, is the number of components in G minus S. This is the statement of the theorem. Okay. So what is the statement? If a graph G is Hamiltonian, suppose that the graph is already given, it is Hamiltonian. If G is Hamiltonian, then for every non-empty proper subset S of the vertex set Vg, the number of components in G minus S is always less than or equal to the number of elements in S. This is the result. If G is Hamiltonian, then G satisfies this condition. Okay. So how to prove this result? As I said, there is no general characterization. So it is one of the we can say necessary condition for Hamiltonian graphs, you can say. First we consider, let G be a Hamiltonian graph, because it is given in the statement that G be a Hamiltonian graph. Okay. So G is Hamiltonian. Okay. Let G be a Hamiltonian graph. Okay. Now we consider one proper subset S, which is a proper subset of the vertex set of G, which is the proper subset of the vertex set of G. Okay. Now, then, if we delete these number of elements in the vertex set, then what we will get? We will get a graph G minus S. G minus S. Where G minus S has how many components? Is the number of components in G minus S. So therefore, it has got how many components? Say n components. Okay. So what I am going to say, let G be a Hamiltonian graph. If G is Hamiltonian and we are considering one subset S of the vertex at S. Since G is Hamiltonian, obviously there exists a Hamiltonian cycle. Obviously there exists a Hamiltonian cycle. Say C. Okay. As I said, there is a cycle containing all vertices of the graph. Say it is V1, V2, and so on and so forth, Vn, and at last V1, because we have to come back to the same starting point. Okay. So what is given the statement? G is a Hamiltonian graph. When G is Hamiltonian, definitely there exists a Hamiltonian cycle C. Say this is the Hamiltonian cycle. Okay. Now, if I consider the graph G minus S, that is the deleting S number of elements or the elements of S from the graph G, what we'll get? We will get a graph, a disconnected graph, you can say, containing how many components? Say n components. Okay, so that we are going to say. Let S be a proper subset of the vertex at Vg. Suppose this one. Yes, let me first say, suppose the number of components in the graph G minus S is equal to n. Say the number of components equal to n. Then the graph G minus S has how many components? N components. Say this is one component, say G1. Say this is another component, say G2. Like that, there are components. Say this is the component Gi, and say this is the component Gn. So there are n components. Okay. Next, let Ui be one vertex which lies in the component Gi. Suppose Ui be the vertex which lies on the component Gi. U1 in G1, U2 in G2, like that. Ui is in Gi, where 1 is less than or equal to I is less than or equal to, what you can say, n. Okay. So this is one vertex we have considered in the component Gi. Then be the last vertex of C. Suppose this is the last vertex of the Hamiltonian cycle C, which belongs to the component Gi, and let Vi be the vertex that immediately follows Ui on C. Let Vi be the vertex which immediately follows from Ui. Okay. Therefore, what we can say, Vi be the vertex that immediately follows Ui on the Hamiltonian cycle C. Clearly, Vi belongs to yes. Clearly, Vi belongs to yes for each I. Okay, and Vj not equal to Vk for some j not equal to k. That is two distinct vertices. Vj and Vk are two distinct vertices. Okay. Hence, there are at least, what we can say, if this is the case, hence there are at least as many vertices in S as there are components in G minus S. So, which concludes the statement, what we said, which concludes the number of components in G minus S is always less than or equal to the number of elements in S, where S is one proper subset of G. So this is a proof of the theorem. So we take one example, counter example for this to understand the statement of the, or how to apply this statement to one particular example. That we are going to see now. So we consider one simple example here. So that example is, you know already the complete bipartite graph KMN example. prove that prove that the complete bipartite graph KMN is non-Hamiltonian. Is non-Hamiltonian. It is not Hamiltonian, it is non-Hamiltonian. For m less than n. For m less than n. Okay. So this we have to prove. We are trying to prove for, you can say, solution. So what is given? KMN. It is a complete bipartite graph where m is less than n. Okay. In this case, this graph is non-Hamiltonian. Okay. Anyway, we know the definition of a complete bipartite graph. A graph is said to be complete bipartite if it is possible to partition the vertex set capital V, vertex set capital V of the graph into two disjoint subsets V1 and V2. These are subsets V1 and V2 in which each vertex of V1 is adjacent or with every vertex of V2. Okay, or you can say every vertex of V1 is adjacent with each vertex of V2. So this is the definition of a complete bipartite graph. Okay, now instead of the graph, it is given as KMN. Okay, particular graph. Okay, this is complete bipartite graph with MN. It implies total number of vertices in this graph m plus n. Okay, so totally in the graph KMN, how many vertices are there? M plus n vertices. So this graph is partitioned into two disjoint subsets V1 and V2, in which V1 contains m vertices and V2 contains n vertices. So like this, this is the proper subset V1, these are the proper subset V2. Okay, if I consider some vertices here, some vertices, okay, there are m vertices. So like this, there are n vertices, which implies every vertex is adjacent with all other vertices, like this. Similarly, okay, so this is the definition. Similarly, this definition. Okay. Now, if I consider S is equal to m, that is, S is the proper subset of the vertex set V. Okay. Then that is there are m elements, that is the number of elements in S is equal to m. Okay. Now, what would be G minus S? If this is the graph G, whose vertex set is V. Okay. So what would be G minus S? If I delete all the elements, because there are m elements in one set. So now the set is also S, which contains m elements. If I totally delete all these vertices, it implies you are going to get a disconnected graph containing how many vertices? N vertices. So there are n vertices. That is 1, 2, 3 like that. There are n vertices. It implies we got a totally disconnected graph in which there are n vertices. It implies the number of components in G minus S is equal to n. But the previous theorem says, but n is greater than m, because as per the statement, it is greater than m. But in the previous theorem, it says if the number of components in G minus S is less than mod of S, or you can see the number of elements in S. But here it is greater than n. So greater than m. Though it is n, because there are n components, but n is greater than m. So by applying the previous theorem, what we can say, if it is less than n, or it would be mod of S. It would be mod of S. But in this case, n is greater than m. So it implies, according to the previous theorem, what we can say, if it would have been less than m, it would have been a Hamiltonian graph. But in this case, it violates the condition, or you can say it is greater than m. So therefore, as per the previous theorem, what we can say, this graph is a non-Hamiltonian graph. Therefore, this is the simple proof, or you can say application of the previous result on this particular graph. With this, we conclude today's lecture. We see some other properties, necessary and sufficient condition for Hamiltonian graphs, because as I said, till today there is no general characterization for the Hamiltonian graph, but we discuss some necessary and sufficient conditions. Okay, so with this we conclude today's lecture. Thank you.